Okay, another vocab here. This is called a chord. Chord. So a chord is a segment whose endpoints are both on the circle. So here's a chord right here. Chord. P, Q. So it's not a line, it doesn't cut through the circle, it stops right here. Here's an endpoint here and here. Both its endpoints are on the circle. So, for example, if I draw a line straight through the center, ooh, that's bad, straight through the center, look, his endpoints are right here. You don't have to draw the endpoints. But we call this guy a diameter. Remember, he goes straight through the center. So a diameter is a chord. Right? A diameter is a chord. Both its endpoints are on the circle. But not every chord has to be a diameter. In other words, look at this chord PQ. He doesn't go through the center. He's not a diameter. Okay, so every diameter like this is a chord. Endpoints right here. But not every chord is a diameter. All right, so theorem 12-4. What do we know about central angles, chords, and arcs? So if we have congruent central angles, then the chords are also going to be congruent. Okay, if we have congruent central angles, then we have congruent chords. We also know that congruent chords will have congruent arcs. And we know that congruent arcs will have congruent central angles. So they're kind of like a big loop here. So angles go to the chords go to the arcs go to central angles. Let's just take a look at this problem. We have circle O is congruent to circle P. Circle O is congruent to circle P. They're exactly the same size. Given that arc BC, so let's just put the rainbow here, is congruent to arc DF. So where is that? Arc BC is congruent to arc DF. What can we conclude? Well, what do we have here? We have congruent arcs. Well, congruent arcs means that I also have congruent central angles. So what is the central angle that goes with this intercepted arc? Well, that would be this guy right here. So we know that angle BOC is congruent to, angle, well, who's the central angle of this one? Angle DPF. All right, so we got the central angles covered, so arcs and central angles. But remember, if you have central angles, you also have congruent chords. So what is the chord that goes with this central angle? It is this guy. So we know that chord BC is congruent to chord DF. Okay, let's take a look here. Theorem 12-5. So within a circle or in congruent circles, chords that are equidistant from the center are congruent. Chords that are equidistant from the center are congruent. So equidistant, remember, means equal, means same distance. So they're the same distance from the center, then they are congruent. Finally, the second part, congruent chords are equidistant from the center. Right? Congruent chords are equidistant from the center. So it's just basically the converse of part one. So this one says, if they're equidistant from the center, then they are congruent. Part two says, if they are congruent, then they're equidistant from the center. So they're just the converse. So let's take a look at what that would mean here. Come on now. There we go. Okay. So here we go. We want to find A here. Oh, let's see. This is remember, A is a chord. A is a chord because he has his endpoints on the circle. This is a chord here. Well, what do we know here? Well, oh, look, I've got this center, and these two lines here, so they're 9 and 9. That means that A and this PR, they are equidistant. They're equidistant from the center. What does it tell us about equidistant chords from the center? That means that they are congruent. So A is congruent to, check that A is congruent to this PR. A is congruent to PR. And what is PR? Well, let's see, this is 12.5 tick. Here's another tick, so this would also be 12.5. So would the total distance be 12.5 plus 12.5? 12 plus 12 is 24. 0.5 plus 0.5 is 1. 24 plus 1 equals 25. So A is 25. Again, they're equidistant from the center, so the chords are congruent. Let's take a look here. This would be the reverse version. So this time, we want to find this part, this distance. What is this distance going to be? Well, I've got a chord here, and I've got a chord here. Looking at these two chords, are they congruent? Are they congruent? Well, 18 plus 18 total gives us 36. This is 36, so yes, these two chords are congruent. So remember, it's the converse. So the original says if they're equidistant from the center, then the chords are congruent. This one says if the chords are congruent, then these chords are equidistant from the center, equal distance from the center. So here's the center. So if this is a distance of 16, forming 90 degrees here, then x must also be a distance of, x must also be 16 because it is equidistant. Okay? All right, moving on. Theorem 12-6. In a circle, a diameter, so that's the key word, a diameter, that is perpendicular to a chord. So a diameter that's perpendicular to a chord bisects the chord and its arcs. Okay? Diameter is perpendicular to a chord bisects the chord and its arcs. So let's take a look at how we could apply that. And when they say diameter, they really mean kind of any segment from the center. Any segment from the center. Because if you look, this problem doesn't really have a diameter. I mean, you can imagine the diameter kind of coming like this, but really they just mean this guy right here. You could think of him as a diameter, kind of shooting through all the way, but really it's just this segment. If it's perpendicular to a chord, oh, here it is. Yes, it is perpendicular to a chord. Where is that chord? Right here. The chord has both endpoints on the circle, which this guy does. So if it is perpendicular to that chord, it bisects the chord. Right? So because we see the segment is perpendicular to chord LM, we know that the segment bisects LM, cuts it in half. So now we can solve for R. So if it bisects it, that means I could say tick, tick by the definition of bisector. And since 14 got split in half, that would mean that this would be 7 and this would be 7. So now I've got this little triangle here that I could use. And by the way, sometimes these will have R kind of like floating around like this, or like wherever, but you just kind of swing it back down and really you just have R here. It makes a triangle. So you have R, you have 7, and you have 3. And this is a right triangle. So you have R, 7, and 3. And remember, you can solve for this third side by using the Pythagorean theorem. So let's solve for R. So we know that A squared, so we have a right triangle. Only because we have a right triangle, we can say A squared plus B squared equals C squared. So our A could be either one of these, so 3 squared plus our B, 7 squared, not 14. It's bisected. It's not 14, it's 7. Equals R squared, right, our C squared. So 9 plus 49 equals R squared. 49 plus 9, 49 plus 10 is 59, so subtract 1, so 58 equals R squared. square root both of these guys. Let's flip that. So r equals the square root of 58. Now let's see if we can break down 58 at all. 58, we factor that. So 58 is going to be, let's see, 2 times, how many times does 2 go into 58? 2 goes into 50 25 times, so, and 2 goes into 8 4 times, so 29. Now, doesn't look like we can do anything with this, so we'll just leave it at that. Square root of 58, we won't simplify it further. If we had a calculator, we could go ahead and punch that in, but I won't make you guys do that for now. So square root of 58 centimeters. Okay, theorem 12-7. Now this is kind of the this is the converse of the previous one. So the previous one says if the diameter is perpendicular, then it bisects the chord. This one we're going to go backwards. It says if a diameter bisects the chord, is not the diameter, then it is perpendicular. Okay, so the last one said if it's perpendicular, then it bisects the chord. This one's saying if the diameter bisects the chord, then it's perpendicular. Okay, so first off, let's apply the problem here first. So come down with this one. So look here, we've got this, and again, they say diameter, but really it doesn't have to be diameter. It's anything that's coming from the center, any segment coming from the center. So here's the center, and I've got this segment coming from there. And you can see how it's bisecting this chord right here. This chord got bisected, right? 11 and 11. So it says if it bisects the chord, then we know it is perpendicular to that chord. Right? We know it is perpendicular. So angle BCA, since BC bisects, we know that BCA is 90 degrees, right? Angle BCA is 90 degrees, and this is also 90, but we'll focus on this. Okay, so how can we solve for y? Again, we could use the Pythagorean theorem to look here and use this triangle here. We could say a squared plus b squared equals c squared. Our a, 11 squared plus our b, y squared plus our c, 15 squared. 11 times 11, 121, plus y squared equals 15 squared. 15 times 15. Let me do that box again. So 15 times 15. What is the total of this box here? Let me break it down. 15 I'm going to break down into 10 plus 5. 10 plus 5. What is 15 times 15? That's 100. 50. 10 times 5 is 50. 5 times 5 is 25. So total is 100. That's 200. So 100 plus 100, 225. So 15 squared is 225. We'll subtract 121 from both sides. So y squared equals 5 minus 1 is 4. 2 tens minus 2 tens is 0 tens, and 200s minus 100 is 100. So y squared equals the square root of 104. So y equals the square root of 104. Let's see if we can simplify that. See, 104, if we break that down, that would be 2 times, let's see, 2 goes into 100 50 times. 2 goes into 4 2 times, so 52. Let's see, 52 can be factored into 2 times. Let's see, 2 goes into 50 25 times. 2 goes into 2 one more time, so 25 plus 1, so 26. And you can check that, 22 times 26. Let's see, and that's going to be 2 times 13. And we can't break that down anymore, but we could say, okay, so y equals the square root of 2 times 2 times 2 times 13. Which we can take out this guy. So y equals 2 times the square root of, who's left over, 26. 2 root 26. Now, as for the proof, why is this true? I mean, I've been saying all this. Why is it that when you bisect it, you get something perpendicular? Okay, let's do a quick proof here. So, prove that if QR, this diameter, or any segment from the center, bisects this chord US, then we want to prove that this guy, QR, oops, I see, we're just trying to prove it, never mind. Come back to me. So if we want to bisect, so if QR bisects US, that means by definition of a bisector, we're doing a kind of short version here, that this is congruent to this, right? This chord got bisected, right? So he bisected it, so he split it in half, so we can say that, let me erase this, sorry. Ooh, it erases that too, all right. Then we get UR is congruent to RS. Let's see, what else do we know? Now, because radiuses, or radii, it's plural of radiuses, we call radii actually, just like cactuses or cacti, are always congruent, right? It doesn't matter whether you go from here, like up to here, or from here to here, or from here to here. That's always congruent, right? So these are also congruent. So you know that TU is congruent to TS. TU is congruent to TS. So let's put a double tick here. All right, so, oh, and also don't forget, so we're trying to take a look at these guys. If I draw this line right here, I've got two different triangles, right? I've got two different triangles. By the reflexive property, I know that TV is congruent to TV. So look at these two triangles. They are clearly congruent by side, side, side. So we know that triangle, we know the triangle TUV is congruent to triangle TUV is congruent to TSB. Why is that? By SSS, side, side, side. So now remember, if the triangles are congruent, all the parts are congruent by CPCTC. So for example, we could say something like S is congruent to U, but that's not very helpful to us. But we also know that this angle right here, angle TVU, is congruent, well, it's red, because that's the important part, red. TVU is congruent to TVS. Right? Why are they congruent? It's because corresponding parts of congruent triangles are congruent. But now let's take a look at this. Since the total is 180, right, it's a straight line, and these guys are congruent to each other, what does that really mean? It means that both of these angles must be 90 degrees. Right? They must both be 90 degrees. Right? Because we have congruent triangles, the total is 180. Since these are equal to each other, it must be 90 and 90. 90 plus 90 makes 180. So we've just proven that if we have a bisector here, we have perpendicular here. Okay, so continuing on, let's keep practicing with this one. So again, theorem 12-7, we talked about if a chord is perpendicular, sorry, 12-6. 12-6, we talked about if a chord is perpendicular, then it bisects the chord. 12-7, we talked about if it bisects the chord, then it's perpendicular. Let's take a look, see what we got here. So we've got, it doesn't have to be diameter, just anything coming from the center. Got this guy coming through, and oh, he's not bisecting, he is perpendicular. All right, so he's perpendicular to this chord. It's a chord because endpoints are on the circle. So since this segment is perpendicular to the chord, we know that the segment also bisects the chord. All right. So, what does this mean? This one's kind of tricky. This is 4. This whole thing is x. This whole thing is x. I mean, it might be easier If this whole thing was like, I don't know, 10, right? This would be 5 and 5, right? If this whole thing was 10, this would be 5 and 5. If it was like 6, it would be 3 and 3, or whatever. But what do we do if it's x? Well, if the whole thing is x, what are you doing to get this? You're just going to divide it into 2. So this is going to be x over 2, x divided by 2, and x divided by 2. If you add up x over 2, 1/2 x and 1/2 x, you get 1 full x. So that's what we've got to work with this one. This one's pretty tricky. We can now, again, because we have perpendicular, we use Pythagorean theorem. We can say a squared plus b squared equals c squared. But we have to be careful here. Our a is this thing right here. So I'm going to put it in parentheses so we don't get x over 2 squared plus 4 squared equals 6.8 squared. Alright, so x over 2 squared. So let me just, x over 2 is really the same. X over 2 is the same as 1/2 x. Right? What is x over 2 squared? It means x over 2 times itself twice, right? So it's x over 2 times x over 2. So what happens when you have 1/2 x squared? It's the same thing. 1/2 times 1/2. What is 1/2 times 1/2? You have half of a half. You have x over 4, right? And then x times x, x squared. Sorry, x squared over 4. So 1/2 times 1/2 is, you can either write like this, or this. They're the same thing, right? 1/4 x squared or x squared over 4. Either way. X squared over 2 squared is 4. Don't forget that. It's not 2. Plus 16 equals 6.8 squared. Okay, 6.8 times 6.8. Let's see. I'm just pretend they're 68ths for now. 8 times 8 is 64. 6 times 8 is 48. 48 plus 6 is 54. Add the 0. 6 times 8 is 48. 6 times 6 is 36 plus another 4. So 40. So 4. 4 plus 8 is 12. 5 plus 1 is 6. And 4. So 46. And then we're going to we move the decimal 2 times, right? So let's move the decimal 1, 2. 46.24. Sorry, it's hard to see. If we subtract 16 from both sides, get x squared over 4 equals, well, we have, you can put 0.00 if you want here, so we just have 0.24. 46 minus 16, so 6 minus 6, 6 tens minus 6 tens is 0. 6 ones minus 6 ones. 4 tens minus 1 10 is 3 tens, so 30.24. Multiply this by 4. Right, we're going to multiply both sides by 4. 4 makes 1, so we get x squared equals 30.24 times 4. So what is 30.24 times 4? I'll just put it over here. We'll move the decimal over twice afterwards. So 4 times 4 is 16. 4 times 2 is 8, plus 1 is 9. 4 times 0 is 0. 4 times 3 is 12. And we're going to move the decimal 120.96. So we're going to square root that. X equals the square root of 120.96. And if you punch that on your calculator, just go ahead and do that. 120.96 square root is 3.6. You could try that on your calculator as well. So that was a challenge problem. All right, theorem 12-8, we're not going to work with this one too much. If you have a perpendicular bisector, it's going to be containing the center of the circle. Right? So any perpendicular bisector of a chord, so if you want to draw a picture here, if you've got a chord here, any chord, let's draw this guy. So if you think about it, how would I bisect this chord? Going like this, no, that wouldn't cut it in half. Going like this, no, that wouldn't cut it in half. You can see it kind of makes sense. You would have to go through the center of the circle. Right? Any perpendicular bisector, is going to have to go through the center of the circle. That's all it's saying. Okay, so let's talk about chords and arcs. So we talked about tangent before. Remember, a tangent is going to be something. This is a tangent. A tangent, you don't have to write this, just a quick review. Tangent line is one that just touches the circle once, right? Just once. A chord has both endpoints on the circle. Right? Chord has both endpoints on the circle. So a chord is going to be something like that, right? That's a chord. Chords, right? Chords equidistant. We talked about this. Chords equidistant from the center are congruent. Right? So if they're equidistant from the center, then they're congruent. And the converse also. Chords that are congruent are equidistant from the center. So both of those are true. If it's equidistant from the center, then they're congruent. If they're congruent, then they're equidistant from the center. We also have another pair of theorems we've talked about. If a segment bisects a chord, then it is perpendicular. I'll just put the sign here. Perpendicular. Erase this. There you go. Perpendicular to the chord. Right? Makes 90 degrees. On the other hand, the converse is also true. If a segment is perpendicular to the chord, then it bisects the chord. So just two different things to keep in mind. If it bisects, then it's perpendicular. If it's perpendicular, then it's bisects. If it's equidistant, then it's congruent. If it's congruent, then it's equidistant. So a little bit confusing, but you'll get the hang of it soon. Let's take a look here and see what we have. We've got some kind of segment here. Right, here is a diameter, and it looks like, I'll make the chord in green. Here's this chord. Look, he has both endpoints. Both endpoints are on the circle. Right, this is a chord. What do we have here? What does this red thing mean? It means it is perpendicular. So if the segment, this blue segment, is perpendicular to the chord, which it is, then we know it bisects the chord. It bisects, so we could put a tick here. If it's perpendicular, then it bisects. So if it bisects, then x must also equal 14. X equals 14. If it's perpendicular, then it bisects. Okay, let's take a look at number 4. So last time we had a diameter. It can be a radius though. So here's a radius. It doesn't have to be a diameter. So here's a radius. And again, here is our chord. He has both endpoints on the circle. You don't have to draw those. Whoa. All right, there's our chord. Yeah, here we go. Okay, so there's our chord. If it's perpendicular to the chord, which it is, then we talk about it bisects. So we can put a tick here. If it's perpendicular, then it bisects. X equals 12. So a lot of these are pretty simple. If it's perpendicular, then it bisects. Now, others take a little bit more work. Ooh, all right, let's take a look now. So let's mark our segment here. This is a radius. Well, we can actually do a couple things. We could say, all right, here is a chord, right? Its endpoints are on the circle. Right, this is a chord. The chord is perpendicular to this segment right here, so we know that this segment is, since it's perpendicular, is going to bisect, so we could put a tick here. So a couple things. You could make a triangle like this. You can make a triangle and say that, okay, this must be, you could say, all right, a squared, so 8 squared plus 15 squared equals, and then you can call this, I don't know, y squared, and then y would just be double x. But actually, you can do something a little bit easier than that. Let me look at it in red. X is what we're asking for. X is just simply the diameter. Right? X is the diameter here. Don't we know the radius already? It is given to, look at this. We know the radius. Look at this radius. This radius is going to be 8 plus 9. Well, what is 8 plus 9? 8 plus 9 is going to be, this whole thing is 17. So this whole thing is 17. If this whole thing is 17, remember radius is the same anywhere you put it. So I mean, you could put a radius up here. That would be 17. You could put it over here. So this would be 17. You don't have to do the Pythagorean theorem. You're going to get that y equals 17. You can do the work here. You're going to see that y equals 17. So if this is 17, then going out this way would also be 17. So we know that the radius is 17, so the diameter is just double that. 17 plus 17, or 17 times 2, x equals 34. So this problem, you could have done the Pythagorean theorem and then doubled it, but you didn't even have to. You notice that, hey, I know that the radius is 8 plus 9, or 17, and I work with that. So it doesn't always, you don't always have to do the hardest way. I mean, sometimes you do, but other times it's a little bit easier. Let's try number 9 here, going into my even odd thing, but let's take a look at this one. So we just talked about how if we have some kind of segment, like this guy right here, and we've got our chord, right? Our chord has both its endpoints on the circle, right? So this is our chord. And he's perpendicular here, so this segment, whether it's a radius or a diameter or whatever, is perpendicular to the chord. We know then it bisects the chord. Okay, so this is 12.6. So unfortunately that's not what we want here. We want this piece x. So this is a tricky one. How can we find just this thing here, x? Well, I know that this whole blue thing, I know this whole blue radius here is the same as this radius here, right? Both of these are the same length because the radius is always the same. So this total length is 15.5. So if we could just find, what this is, let's call him y. If we could find what this is, we could find what x is, because we know that x plus y is going to be the same as this, 15.5, right? So if we can find y, then we can figure out the answer here. So, like I said, you can take a radius and you can rotate anywhere. I mean, this is going to be 15.5, you don't have to draw it. This is 15.5, this is 15.5, but let me erase those so it doesn't add too much to this. You can take that, basically, and draw the radius anywhere, and it's going to be the same. So, oops, oh well. Let's take this guy and kind of swing him around so that it makes a nice triangle over here. All right, that is 15.5. So go ahead and draw that line in here. And we know that this is 90 degrees. So what we have here is we have a nice, again, right triangle. We can use Pythagorean theorem to find y. And if I found y, then I can find x. So again, we're going to use a squared plus b squared equals c squared. So we'll use y squared for a. You could use the other one as well. Plus 12.6 squared. 12.6. That's a 12. Sorry. 12.6 squared equals c squared. The hypotenuse is 15.5. And if I give you too many decimals, you can just use a calculator. So why don't we just go ahead and show this for the first time here. What is 12.6, nope, 12.6, and then squared. So that's 158.76 equals, Let's bring back the calculator here. 15.5 squared. 15.5 squared. 240.25. 0.25. Okay, so then we'll get y here by, let's get rid of this guy, so we'll subtract 158.76. Okay, we'll do this one by hand, so y squared equals, let's see, 5 minus 6, no, so it's going to bother us to 1. So 15 minus 6 is going to give us, let's see, 15 minus 6 gives us 9. 1, we cannot borrow from here. So this 40 is going to become 39. Now we have 11 here. 11 minus 7 is 4. 9 minus 8, 1. 3 minus 5 cannot, so we'll borrow from those hundreds. 13 minus 5 is 8. So we get 81.49. 81.49. And from there, all we've got to do is take our square root. Let me go ahead and do that in red. Square root of 81.49, so y equals, you can write it as the square root of 81.49, or let's see if we can get an approximation here. 81.49 square root. Alright, so why don't we go ahead and put it as an approximation? Approximately 9.027. So approximately 9.027. Approximately. Okay, so if this is 9.027 and this whole thing is 15.5, right? So to find x, we just say 15.5, which is the radius, 15.5 minus 9.027 will give us approximately x. Okay, so again we have x plus y equals 15.5. You don't have to do it algebraically like this, but we'll put substitute in 9.027. It's 15.5. We'll subtract out 9.027. Alright, and since we're running out of time, let's go ahead and just do this with the calculator. 15.5 minus 9.027. 15.5 minus 9.027. 6.473. So 6.473. And I should make that squiggly because it's just approximately 6.473. To finish up, we didn't, this program I used to generate these didn't quite have everything I needed. So we have the rest of this page. Let's do two more quick problems here. So again, we're solving for x. We've got these chords. So just draw a circle. Doesn't have to be a beautiful, perfect circle like that, but give it a center. And let's say we have, draw two lines like this coming out, and then draw two chords that are perpendicular to those lines. Chords that are perpendicular. Okay, so you got center, two lines coming out, and then two chords. The chord intersects the circle twice at its endpoints, and they're perpendicular, right? That's how we measure distance, is perpendicular lines. And let's say this is 6, and this is 6. And let's say you've got 15 here and x. Okay, so just get that set up. What would x be? So this is a kind of a simple problem, but it's not really in any of the ones we practiced. Basically, the idea is just using the converse. Remember, we talked about how if the chords are equidistant, if the chords, so this is a chord, remember these two are chords here, if this chord and this chord are equidistant from the center, which they are, 6 and 6, right? You can put a tick here, tick if you want. If they're equidistant, then these two are going to be congruent to each other. So in this case, x is just 15. Okay, x is 15. So if the chords are equidistant from the center, then they are congruent. And of course the converse. If they are congruent, then they're equidistant from the center. Don't forget about that type as well. All right, last one here. Let's call this number 11. Draw a circle, center. Let's say we have 14 as our radius. Let's say this is 5, and let's say you've got here like that as x. And don't forget to add perpendicular. So go ahead and set that up. Mine kind of looks like a potato, but that's okay. All right, so what are we going to do for x here? So remember what we talked about. If a segment is perpendicular with a chord, then it's going to bisect, right? It's going to bisect the chord. So this is going to be tick, tick. So here's the thing. If this whole thing is x, again, this is going to be x over 2. And we already did that actually in the practice problem. So why don't we call it, instead of x over 2, why don't we call it 1/2 x? We'll call this 1/2 x. You can do x over 2 or 1/2 x. It doesn't really matter. They're the same thing. Okay, and now let's take this guy, and since it's a radius, I mean, this could be 14, this could be 14. Don't draw it there. Draw it here. Swing it down this way. So this is 14. Okay, I'm going to erase this. Okay, and we've got a nice right triangle here. So let's go ahead and find x using not x, but 1/2 x. So we're going to use a squared plus b squared equals c squared. A squared plus b squared equals c squared. So let's say 5 squared plus 1/2 x squared. All right, 5 squared plus 1/2 x squared equals 14 squared. 5 squared plus 1/2 x squared equals 14 squared. 5 squared is 25. Now, 1/2 times 1/2. Remember, squared means 1/2 x times 1/2 x. What is 1/2 times 1/2? 1/2, half of a half. Like, if you have half a pie, half again, you have 1/4. Right? 1 times 1 is 1. 2 times 2 is 4. X times x is x squared. Equals 14 squared. 14 times 14. 16, 5, 0, 4, 1. That's going to give us 196. Okay, subtract 25 on both sides. 1/4 x squared equals 6 minus 5 is 1, 9 tens minus 2 tens is 7 tens, and 100. Now to get rid of this 1/4, remember you're dividing by 4. What's the opposite of dividing by 4? Multiplying both sides by 4. 4 over 4 makes an equivalent form of 1. So we're going to get x squared equals, let's just go and multiply. 4 times 100 is 400. 4 times 70, so 400. 4 times 70 is 280. And 4 times 1 is 4. So we're going to get 684. 684. Then we're going to go ahead and square root both sides. We're going to get x equals, now we could break down 684, look for common factors, etc., etc. Since we already have our calculator out this lesson, why don't we just go ahead and get the decimal version of that. 684 square root approximately 26.153. So why don't we go ahead and add the approximate. What was that? 26.153. So if you got a calculator, as long as you put these curly signs means approximate, you've got your answer.